Okay, let's go ahead and go back to what we've learned about limits thus far. Remember that I said that with limits, we aren't necessarily focused with what's going on at that exact point. We're more concerned with what's going on around it. And it sounds like I'm contradicting myself, but if you just follow me for a minute here, you'll kind of get the hang of what limits are in general. So, first of all, I gave you a geometric example of what a limit is. I discussed that if we have a circle and we placed a polygon within that circle, we came with the hypothesis that as the number of sides increased, then the closer and closer that polygon inside the circle became to being a circle. So with that said, we provided three statements. The first one was as n gets larger, then your n-gon gets closer to being a circle. Then we actually made a more general hypothesis and we said, well, as n approaches infinity, then your n-gon approaches the circle. And then we wrote a mathematical statement saying that the limit of the n-gon, in other words, the only shape that it can possibly remotely become close to would be the circle. And this part right here is the way we represent in math terms as to what we mean when we take the limit of something. And that was a more general description of what a limit is. If you can see here, the limit of any function as x approaches a certain point A is equal to L, which in this case is the limit. And then I also discussed that with limits, we approach from the right-hand side. We denote that with a superscript of a plus sign. And then we also approach it from the left-hand side, and we denote it with a superscript of a minus sign. So in other words, if you think about it, if we approach, let's say, 7 from the right-hand side, that means that it could be any number on the right of 7. So, for example, that would be 8, 9, 10, 11, 12, and so on. Also, that doesn't necessarily mean that it has to be a whole number. It can be 7.01, 7.0001, 7.000001, etc. So, as long as it's to the right, then we denote it with a superscript of a plus sign. Also, for the left-hand side, it's the same concept. For example, if we approach x, if we approach 7 from the left-hand side, then that means it could be anything on the left of 7, such as -5, -4, -3, -2, -1, 0. And then it could also be 6.9, 6.99, 6.999. So, again, as long as you're able to distinguish what's on the left and what's on the right, you'd be perfectly fine with this concept. Okay, I also introduced to you this theorem, and it says, as x approaches a, the limit of f of x is L if the limit from the left exists and the limit from the right exists, and both limits are L. That is, so in other words, you don't even have to write the word part of this theorem down. You actually need to write this part where it starts with if and then everything underneath that. Basically what this is saying, and this theorem is usually applied to graphically, so whenever you're taking the limit of something and you're provided a graph, or if you are given a piecewise function. If you don't remember what a piecewise function is, remember it's a function that is broken up into pieces. That's why it's called a piecewise function. So in other words, cases. Basically what this is saying is if you're going to take your overall limit of something, so this is your overall limit right here, it says the limit of f of x as x approaches a equals L. Well, before you can even say that, you have to take the limit from the left and you have to take the limit from the right, as in case 1 and case 2. Now, what's important about these is that both of these limits, the one from the left and the one from the right, have to both be the same. They have to be equal to one another. If they are not equal, then your overall limit does not exist. However, if they are both equal, then you can say that your overall limit does exist and it is whatever value both case 1 and case 2 are equal to. So for example, if your limit of f of x as x approaches a from the left is 3, and your limit of f of x as x approaches a from the right is 3, then you know that your limit of f of x as x approaches 3, or a, or whatever we approached, I forgot already, equals to 3. So in other words, if both of these are the same value, then your overall limit is the same value. However, if for case 1, from the left-hand side, your answer was 5, and for case 2, from the right-hand side, your answer was 6, then since 5 and 6 are not equal to each other, your limit overall would be does not exist. So this is a very important theorem, and you use it a lot with piecewise functions or graphs that are provided to you. So let's take a look. I'm going to go back and forth, so let's actually continue. Let's continue with this one. It says, graphs can be used to determine the limit of a function. Find the following limits. So for example, I have a function. It says the limit of x squared minus 1 over x minus 1 as x approaches 1. And I'm giving you the graph. Find the limit. Well, the first thing you need to see in this case is there is an open circle at x equals 1. And if you think about it, why is there an open circle at x equals 1? Well, if you were to plug in 1 back into this function, actually, let's recall, what kind of function is this? Okay, this is a rational function because it's a polynomial over a polynomial. And remember, with rational functions, there was one stipulation. It said that the denominator cannot be equal to 0, because then it would give us division by 0. And you know that it can't happen. So the reason why x equals 1 here has an open circle is because if we plugged in x in here, which is 1, we would get division by 0, and that can't happen. Now, it says find the limit as x approaches 1. Well, the first thing you need to do is look at where x is 1. So in other words, right here, you're going to draw yourself a little vertical line, which I like to call a wall. So draw yourself a vertical line or an up and down line that goes through x equals 1. Now, remember, before we approach from the left, before we take the overall limit, we have to approach from the left and from the right. So if you have your wall up here, and I know you don't see the wall here, but if you're drawing it on your own paper, you're going to see your wall. Let's approach from the left. In other words, to the left of the wall. So if I approach that point, this little circle, from the left, follow my arrow, I'm following him, I'm following it, I'm following it, I'm following it. What is my value for y when I hit the wall? 2. Okay, so again, I'm concerned with my y value. Okay, so my limit as I approach 1 from the left is 2. Now let's approach it from the right. So that's this part of the graph. So if I approach from the right, I'm following it until I get to the wall. I hit the wall right there, and my y value is 2. Exactly. So are both of the values the same for the left and for the right? Yes, they are. Therefore, my overall limit right here is equal to 2. Correct. Yes. Okay, so let's take another function. I know I probably went over this with some of y'all. Not all of my classes, but just hang with me. It'll be a review if you've already heard me say this. But we have a function right here. So as you can see, this is 2 lines, but it's all one function. It says find the limit of h of x as x approaches 1. Well, the first thing you need to do is you need to create your wall at x equals 1, which is going to be this vertical line right here. X equals 1. All of this vertical line. But before I can take the overall limit, I have to take the limit from the left and the limit from the right. Correct. It doesn't matter which way you do it, as long as you do both of them. So let's go ahead and build a wall right here. My limit from the left-hand side. So that means it's this part of the graph right here. So if I approach my wall from the left-hand side, I'm approaching it, I'm approaching it, I'm approaching it. My value from the left-hand side is what? 4. Okay, now I'm going to approach that exact same wall from the right-hand side. So if I approach from the right-hand side, I'm approaching it, and my value for y is -2. Is 4 and -2 equal to each other? No. So my overall limit h of x as x approaches 1 does not exist. So these are the answers. We approached from the left and we discussed that it was 4. We approached from the right and we discussed that it was -2. Therefore, we made that conclusion that my function h of x, the limit of that as x approaches 1, doesn't exist. Okay. You don't have to copy this down. This is basically the method that I'm teaching you. It's an alternative approach. We can draw a wall at x equals 1 as shown in blue on the following graphs. We then follow the curve from left to right with the pencil until we hit the wall and mark the location with an x, assuming it can be determined. Then we follow the curve from right to left until we hit the wall and mark the location with an x. So in other words, we've been doing this. Again, you don't have to write it down because I think it's a definitely easy method to remember. So let's continue. This was example 1 right here. Now we'll continue with example 2. It says it's going to be the same function. If you realize it's h of x. However, I'm approaching -3. So as you can see, this blue line, this blue vertical line, that's my wall. It's at -3. So now let's approach it. However, before I can even discuss what my overall limit is, I have to approach from the left-hand side and I have to approach from the right-hand side. So if I approach from the left-hand side, I'm going to be starting with this small little piece right here. And I'm going to hit the wall. And when I hit the wall, my y value is -4. Now, I'm going to approach from the right-hand side. Well, if you pay close attention, it's the exact same line right here, but I'm approaching from the right-hand side. And when I hit the wall, my y value is -4. So in this case, I didn't even need this piece of the function right here. That was just useless information. So it really depends what value you're approaching to decide if you're going to be using the entire graph or not. So you have to be very careful with what you're approaching. So in this case, since both of my values were -4, I can say that my overall limit of h of x as x approaches -3 is equal to -4. Okay, the next one. I've already have the answers there for you. It says, let's go backwards actually. I'm trying to find the limit of f of x as x approaches 3. So in other words, I go ahead and draw my wall right here at x equals 3. I'm going, before I say what my overall limit is, I have to approach from the left-hand side and I have to approach from the right-hand side. And both of them have to be equal. So if I approach from the left-hand side, that's this part right here, I continue coming down all the way until I hit the wall, and my y value for that function is 4. If I do the same from the right-hand side, I continue until I hit the wall, and then my y value for that function is also 4. 4 is equal to 4, therefore my overall limit is 4. This piece of the hyperbola right here was useless information because I didn't need anything from it. So again, make sure you understand what you're looking at or what you are approaching. Okay, the next part, it says find the limit as x approaches 2, where f of x equals 1, where x cannot equal to 2, and f of x equals 0 when x equals 2. So in other words, we have a function that looks like this. We have f of x equals to 1. So in other words, we have y equals 1, which is a horizontal line going through the y-axis at 1. And we have an open circle at x equals 2 because we know that it's one of our stipulations. Then we have y equals 0 at x equals 2. So in other words, that's a coordinate. So when x equals 2, y equals 0. So it's a shaded in circle right there. All we have is just 1 point. So we're finding the limit as x approaches 2. So if you want to, you go ahead and draw your vertical line right there. And before you take the limit overall, you approach